All right, let's jump right in. Today, we're going to crack a chemical code. We're going to learn the simple, really elegant language chemists use to describe the molecules all around us. Everything from the flavor in cinnamon to the sharp tang of vinegar. Let's get into it. So, take a look at these three things. What on earth could they possibly have in common? I mean, one adds delicious flavor, one strips paint off your nails, and the other is probably sitting in your kitchen cabinet right now. Well, the answer is hidden in their molecular structure, and by the end of this, you'll be able to see that connection as clearly as any chemist. So first, let's wrap our heads around the problem chemists were facing. There are millions and millions of known organic compounds out there. Without a universal language, it would just be complete and utter chaos. Just imagine trying to find a book in a massive library with no catalog system. Yeah, that's what chemistry would be like. And the solution to all that chaos is something called IUPACE nomenclature. Think of it as a standardized, universal language for chemistry. It's a system that makes sure a chemist in Tokyo and a chemist in Toronto are talking about the exact same molecule just by hearing its name. And the best part? It's not about memorizing stuff. It's a language based entirely on structure. Okay, so to learn this language, we're going to start with one fundamental building block, kind of like a master Lego piece. For the molecular families we're looking at today, that core component, that all-important piece, is called the carbonyl group. And here it is. Simple, right? It's just one carbon atom with a double bond to one oxygen atom. This little C double bond O is what we call a functional group, and it is the absolute heart of aldehydes and ketones. You can think of it like the engine in a car. Its presence, and this is really important, its location pretty much determines everything about the molecule's identity and how it behaves. Now, this is where it gets really interesting. Based on where that one little carbonyl group is placed on a carbon chain, we get two completely different families of compounds. It's just a perfect example of how in chemistry, location is everything. Check this out. It's so simple when you see it side by side. If that carbonyl group is sitting at the very end of a carbon chain, congratulations, you've got an aldehyde. And the IUPAC language reflects that by giving it the suffix al. But if that same group is anywhere in the middle of the chain, kind of sandwiched between other carbons, you have a ketone. And its name will end in -one. It's literally that simple. End of the line, it's an aldehyde. In the middle, it's a ketone. And boom, this brings us right back to our original question. That amazing smell of cinnamon? That's from cinnamaldehyde. The delicious flavor of vanilla? That comes from vanillin. Both of them are aldehydes. And the nail polish remover? Well, that's acetone, a classic ketone. Even fructose, the sugar that makes fruit sweet, is a ketone. See? These aren't just abstract drawings. They are literally the molecules of our everyday lives. So we've got aldehydes and ketones, both built around that same carbonyl group. But what happens if we decide to tweak that core piece just a little bit? Well, we can create an entirely new and super important family of molecules. Here's how it works. You just start with a carbonyl group we already know, the good old COO. Then you attach a hydroxyl group. That's just an oxygen bonded to a hydrogen, or OH, to that very same carbon. Put them together and you get a brand new thing, a carboxyl group, which we write as negative COOH. So a carboxyl group is really just a modified carbonyl. Now, any molecule that has this COOH group gets a new family name. It's called a carboxylic acid. And the most famous member of this family, you've definitely met it before. It's acetic acid. That's the molecule that gives vinegar its super sharp, pungent smell and its sour taste. So the secret of vinegar is this very specific functional group. All right, so we've covered the three families and we've seen their real-world connections. Now let's put it all together into a simple summary, basically a cheat sheet for this chemical language. This table right here, this is the key to everything. You can see the pattern so clearly. An aldehyde has a carbonyl at the end and its name ends in -all. A ketone has a carbonyl in the middle and its name ends in -one. And a carboxylic acid has that special carboxyl group and its name gets the suffix oic acid. So that acetic acid in vinegar, its formal IUPAC name is just ethanoic acid. The logic is just crystal clear. So here's the most important thing to take away from all this. Organic nomenclature. It's not just some random list of names you have to memorize for a test. It's a descriptive system. It's a code. If you see the name, you can draw the structure. And if you see the structure, you can figure out the name. They're directly connected. And that really leaves us with a much bigger question, doesn't it? We just saw how a tiny change in structure, just moving a C equals O group from the end of a chain to the middle, creates a completely different substance. So if the name reveals the structure, the next logical step is to ask, what does that structure reveal about why vanilla tastes sweet and vinegar tastes sour? Now that is the power of cracking the code.